everyone. My name is Kamal, and I'm a PhD student at KTH. I'm gonna talk about Karamel, our system, which is about reproducible distributed experiments on cloud. My supervisor is Jim Dowling. He's associate professor in KTH. This work is coordination between KTH and Swedish Institute of Computer Science, and is funded by Biobank Cloud and Community, two European projects. Today my talk is mostly about, I'm going to give you a demo about the system, but first I have some slides as well. So first I'm going to give you some motivation about the work, and then what does reproducibility mean for us. Later I will start my demo in a few minutes because it takes like 30 to 40 minutes, and then I will come back at some point when the demo is running. I will talk about reproducibility, especially in Karamel, how we do it in Karamel, and I will go into the detail of engine of Karamel, how it's designed, and I will talk a little bit about our orchestration mechanism, and in the end I will introduce some more challenges yet to address. All right. As you know, in science, you have to, whatever claim you make, you have to prove it, and it should be reproducible by everyone. There are two ways of proving your claims in science. One is by analytical explanation, or empirical proof. And in computer science, we mostly do empirical proof, like by empirical experimentation. And it's very important to make our work reproducible for everyone else if they want to extend our work, or they want to see if our claims are right. And that's an unavoidable part of science. And especially in distributed systems, it is very important, because in distributed systems, we know it supports many other scientific fields, like big data or genomic kind of research. Therefore, it's very important. It's like hot topic. Distributed system is in the middle of attention nowadays. And that's why we have so many different research tracks in distributed system itself, like scheduling, fault tolerance, scalability, and so forth. And but it's extremely hard, because in distributed systems we have to deal with thousands of nodes, and there are dynamicity of the system, the behavior of the system. System should be elastic. And there are massive of configuration involved in the distributed systems. So reproducing experiments in distributed system is extra hard. So what do we mean exactly with reproducibility? In each experiment, there are three elements involved. First is laboratory, where is the place you do your experiment. Second is the person who does the experiment, it is experimenter. And the third one is apparatus, the way or tools how you measure your results. If you make your experiment in such a way that all these elements can be changed for another, for example, if you can do it in another place, or another person can do it instead of you, or with using other ways of measuring results, we call this experiment reproducible. But if one or some of these, all or some of these elements has to be constant, or has to stay the same, then your experiment is not reproducible. We can just say it's replicable. And our work, Karamel, is towards making experiments reproducible. In computational reproducibility, we came into a conclusion that if you want to translate all these parameters, or some of them, we have to make sure that your infrastructure is reproducible, your software is reproducible, your experiment and your data, all of them are reproducible. So now I'm gonna start showing you how you can make your experiments on Karamel to be reproducible. But first, let me show you what is the experiment that I'm gonna design here. I'm gonna design a simple word count experiment on Apache Flink, and this experiment is to measure performance of the word count on Apache Flink. Therefore, in this cluster, we have 4 nodes. One is the Hadoop name node, or Apache Flink job manager, and we have 3 Hadoop data nodes, or Flink task manager. On each data node, I'm gonna run a random text generator for providing data for word count, because we don't have data, we have to generate it, and I've decided to generate a random text, which is a big file, and it takes a lot of time to generate. So I'm gonna distribute these tasks between all data nodes and do some parallelization here. And then when that is finished, I'm gonna submit a word count job on a data node, on the name node or job manager, and just wait until it finishes. And I will show you in this demo, I will show you different part of Karamel as well. Okay, let's get started with the demo here. If you open your browser and go to our website, karamel.io, you will see here that one menu is getting started. There are a lot of explanation here. You can read it if you're interested. In the Getting Started menu, there is a link for downloading the jar file, latest jar file. I'm going to get the latest jar file. And when you click on this, it will download in your download folder. So if you go to your download folder, you see the tgz file is here. Then you just open your terminal and you go to that folder. From Karamel folder, you can just run bin Karamel command. By running that command, it will bring you to the Karamel page, and I'm going to just increase the resolution a little bit. Okay, here, what Karamel is a standalone web application, a simple application that you can manage your cluster on your own machine. So here, I'm going to just demonstrate how it works, and then I will explain a little bit about insights. So if you go to the menu, you can load cluster definition. Cluster definition for us is just a text file, like a textual representation of your cluster. And we have some examples already in the downloaded binary. As you can see here, there is a folder called examples. From here, you go to the stable clusters. I'm gonna take Flink on HDFS for 3 nodes. So I open this file. When you open your cluster definition, you will see groups of your installation. Okay, we have now in this cluster we have 3 machines, 1 name node and 2 data nodes, as you can see here. And on the name node group, we have we're gonna install Hadoop name node and Flink job manager on top of that. And then on name nodes, I'm gonna install Hadoop data node and Flink task manager. So you can easily change number of nodes here to 3. And then here is the cluster. So, but now I'm gonna, as I said, I'm gonna design that experiment on top of this cluster. For doing that, I just go back to the Karamel website, In the Karamel website, there is a menu called experiments. I have already published all the code we need and some explanation about how you do design your experiment in Karamel. But if you scroll further down, after this, in the second part is a simple experiment measuring performance and word count by Flink, Apache Flink. And you see some code snippets here. So I'm just going to use these code snippets in my designing experiments. Before doing that, go back to Karamel local web interface. From the menu, you can access experiment part. In the experiment part, in Karamel, we use GitHub as artifact server, which means that we publish everything on GitHub, and that is publicly available. So I'm gonna log into my GitHub first. When I log into my GitHub, it will through the GitHub client, we Karamel fetches all the information on your GitHub. So here you have two options. You can either design new experiment or load already designed experiments. So I'm going to design a new experiment here. First, as I said, I want to, I split this experiment into two. First is the text generator, and second is the word count. And I do that because I want word count to be separate, and I'm going to measure just word count time, not the text generator. Well, we can do count text generator time as well, but in this way we can split them. We can measure them separately. So first is the text generator. I call it generator. And you can type some explanation if you want. This generates a big file and copies it into the DFS. And as you can see here, my GitHub repos are already loaded here. I'm gonna use this Karamel Lab repo, and I create my experiment. If you go to the Karamel Lab now, I have already some projects here. I have two projects here, so I'm gonna add those to the same repo as well. So here you can see that there is a big text area that you can write your experiment code here. There are two options. Either you write a bash code or Python code. We support both of them. So I'm gonna write bash. I go back to the website and I copy this bash code from already designed code and put it here and paste it here. So what this code does is as following. First, it tries to remove text input.txt file in the temp folder if it already existed, and then it's gonna, with this command in Linux, urandom, it's gonna generate a 128 megabyte almost a file and put it in the input text. So we create a big file, a file with 128 megabyte size, and we'll put it in input.txt, and then later on it will make sure with hdfs command, it makes sure that slash words does not exist. If it exists, it will remove it, and then with using another hdfs command, copy from local, it copies the input.txt to the slash words slash this variable. This variable comes from a node name. As I explained in my slides, I'm gonna give this task to be run by all the data nodes. So, and all of them gonna copy the file that are generated in this folder. So, and that file has to have unique name, and I use name of the node for make the file's name unique. And this is chef kind of syntax. It will bound this variable later on in runtime. All right. Now this is the code I wanted to write. If I press to save, it will take some time and it will push it into the GitHub. So if we go back to the Karamel lab, we see now that we have this generator code is generated, and it has a cookbook structure. Cookbook, I will explain later. We are building everything on top of Chef, and Chef is a system for installation and configuration, and is dependency aware. And in Chef, each cookbook is a unit of packaging your software. So here we defined a cookbook for our experiment, which is called generator, and it has some recipes. We have two recipes. One is install and one is experiment. This experiment we have designed. As you can see, the code appeared here and in the experiment. And the rest, Karamel fixed them for you. If you are not familiar with writing Chef code, you can just do it via our experiment designer. But we need to further configure our experiment. If you just press on the advanced checkbox here, all right, you see there are three more configuration texts here. That one is orchestration. If you click on orchestration, first we need think about our text generator. What are the dependencies cluster-wide? First, because Karamel does everything from the scratch, here we need to make sure that our Hadoop data nodes are up and running, all of them, before running the text generator, or Hadoop completely up and running. So here I'm going to depend my text generator to Hadoop data node. And now you can recognize this syntax that Hadoop is Hadoop cookbook, and data node is name of the recipe service that is going to be installed. And we have to give more information where this Hadoop cookbook is residing in GitHub. So if you go back to the code snippets that I've written here, we have this part. I just copy it and paste it here to make sure. And I'm using our pre-designed Apache Hadoop cookbook, which is in this Hops Hadoop repo. You can just take a look into Hops Hadoop repo as well. It's a repo that with plenty of known engines, distributed engines like Hadoop, like Spark, like Flink, and they are caramelized. So Karamel knows all of them, and you can use them. We have Yarn here, and so on and so forth. So I'm going to use our own Hadoop because it's already known by Karamel. And that's it. That's pretty much it. That's what we have to do. And we don't need to make any change here now. There are some parameters that we can define. By default, we have user and group that are defined here. I'm going to explain them a little bit more later. But now I just press to save. This and this is also saved, as you can see here. Now I just close this experiment, and I'm going to create new experiment. New experiment is word count. Word count counts a number of words in HDFS file and copies the results into HDFS again. So this experiment, as I said, it will take a prepared file in HDFS, and we'll count number of words in that text file, and we'll write the result into HDFS again. I'm gonna put this in the Karamel lab also. I create it. So we don't need advanced button section yet. So in the word count experiment, I'm gonna copy this bash code that I have written for word count, and I'm gonna explain what it does. When you paste it here, so line by line, first it removes this /counts, because I'm gonna use a /counts folder as for copying results into this folder. So first, to be in the safe side, I just make sure this folder doesn't exist, and then I step into the user local Flink, the installation path of the Flink, because I'm gonna run Flink here, and from the bin folder I run Flink, and I say run it, and I do -p, which means number of parallelization in Flink. And number of parallelization for us is dynamic. It depends, because here I want to design my experiment in a way that if I have 2 nodes or 5 nodes or 10 nodes, I ask Flink to run a word count with the same parallelization factor. And as you can see here, again, this is a parameter that will be bounded by chef in runtime. And this is the jar file, that's J. I take the word count jar file from Apache Flink itself. And this is the last parameter is the HDFS folder. For first we give it the input folder, which is words, as we already know. We created it on the Apache Flink on HDFS, and the second folder is the results. And Flink has to know the IP address of the name node, Hadoop name node, and this is also a parameter here. That's because we don't know in advance, and it depends. It will be changed the IP address. So I just put this parameter here, and a /counts into the counts folder. The results will be copied later. We are done with this one as well. I just press to save it. If you go back again to the Karamel lab, you see that now we have both word count and generator here. All right, I'm going to further customize the word count. First, okay, our word count has to make sure Apache Flink is up and running. So I can say Flink task manager to make sure. Yeah, I'm gonna just copy from there to avoid any misspelling here. So first, our generator is dependent on the Flink task manager, as you can see here. Make sure that in the cluster all the Flink task managers are up and running before we run the word count. And then second, the generator experiment is also finished. So, and then I just need to give the cookbooks on GitHub for this. I tell which Hadoop cookbook and which Flink cookbook has to be used here. And again, we don't need to do anything more here, but you can parameterize. If you have more parameter in your experiment, you can define them here. You can read up more in our website. I just skip this part. I press to save. Okay. Now we are done with the experiment design. I'm gonna just go back to the to our board cluster definition. Here, as you remember, we just loaded the cluster definition. I'm gonna add more recipes here, and the data nodes I'm gonna add the text generator, right? It's enough URL. and just copy this GitHub URL from here and paste it here, and press fetch. It will fetch your cookbook and recipes, and I pick generator experiment, add it to the recipes. So we have generator experiment in this stack now, and I'm gonna add the other one, which was word count, also, and press fetch. It will fetch word count experiment as well. All right, we have word count on the name nodes and generator and experiment. Now, the cool thing is that you can just save your cluster definition. It will save it in your, as you can see here, this is your cluster definition, and you can send it to anyone. We have the cookbooks, word count, and generator, plus Hadoop and Flink here, and then you have your group definitions, and you can send it to anyone, and that person can run the same experiment, and that person can just load it like this. It will load it again. Now, if you just press on the configure, you can further customize your experiment before running it. So here there are two important points that you have to make sure, because we are using 4 different cookbooks, and each cookbook in our design will try to make its own user and group on Linux. So if you run each of them in a separate user, then for example, your word count will not have access to your generator data or into your HDFS. So I'm gonna make sure that everything is, if you open your word count, you see we have word count group and word count user, and it's called word count, the same name. So I'm gonna use the same name for all of them. First for Hadoop HDFS, you see there are a lot of plenty of attributes that you can change them here, but I just leave them as it is. I'm gonna just make sure our user is by default is HDFS. I'm gonna change it to word count, and in the generator as well, I'm gonna change these two to word count, and in the Flink as well. All right, and as you can see in the Flink other parameters, you can just also increase the heap memory of your job manager and task manager, and that's very important. If you want to stress test your Flink, for example, you have to give it enough memory, right? So I'm gonna change it to 3 meg because I'm gonna use EC2 machines, M3 medium machines that they have more than 3 gig memory. So I'm gonna allocate like 3 gigabyte to Flink. I add it. So, and then in the end, you just press launch here. In the launch dialog, we have SSH keeper, and that means if you're using Linux or Mac, it will pick up your default SSH keys from your home folder. But if you don't like that and you don't want to use that, you can just click on advanced, and you can generate keys, and you have to give if your SSH key is password protected, you have to give your password. You can always validate your SSH key, and then in case of using bare metal, you have to give your sudo account that we can, because basically Karamel uses SSH for accessing your machines. I'm gonna leave it as it is. And then in Amazon EC2 part, you have to give your Amazon AWS credentials, and Karamel caches them for you when you put it once. I have it already, so when I put it here, you can just validate them. If your account is valid and every tab is valid, then in the summary you see that everything is valid, and you can just submit it. Then when you submit your cluster, it will bring you to the Karamel terminal, and you can access terminal again in the menu as well here. So in the terminal, it will show you the running clusters. You can just click on the status, and in the status you will see your cluster is ongoing. it's changing phases from, see here, it start to pre-clean your cluster on Amazon EC2, and then it tries to fork groups, security groups, and it did. And it measures every phase for you as well, the duration of phases. Now I'm gonna open my EC2 account. As you can see here, this machine is already running, so we don't. This is not our clusters, but we have 3 machines here. They are being forked. One of them is finished. 2 are being forked. And then, when everything is finished, the Karamel will go on and it will pass the forking machines phase. So we're gonna wait a little bit here. So as you can see, all machines are ready. We have name nodes and 3 data nodes, and we go back to the Karamel. You see here, after you pass the forking machines, it will generate this part, these tables showing status of your cluster, how it's going. And you have some big tables, and you have a smaller table inside. The big table stands for your machine, each machine, and the smaller table is a queue of the tasks inside your machine. So if you scroll down, you can see all your machines and IP address and everything, and the status of your machine is connected and is ongoing. And here you can see that yeah, as you can see, some tasks are started from a waiting status, and then they go to the ongoing. This task, for example, is ongoing now, and when they're finished, it changes to done. And in case it fails, it will show failure. When a task is done, you can access the logs. You can see the logs. If you just press on the logs, yeah, here you can see the logs, and you can always come back from this menu on top to the status again. And also, yeah, I'm going to show you our orchestration tag right now. Orchestration tag shows you a good insight about how your installation is going. So we have to wait just 2 seconds here until your DAG gets expanded. As you can see, it did already. So I'm gonna just make it a little bit smaller because it's quite a big DAG now. Yes. In the DAG, we have many tasks, and each task has a color. So the tasks start from being blue, which means it's waiting, and then it will change to into yellow. It means that that task is ready to go, but the machine hasn't picked it up yet. So it will wait because it's machine serialized running task. And when machine picks up the task and it's ongoing, it will change to the blinking orange. And then when the task is done, it will change to the green color. You can see here our installation is going. And one important thing that you can confirm in your experiment definition and everything is that you can just look at your DAG and see, okay, you expect the last step is your word count experiment. Okay, that's correct. And it depends on, for example, Flink Task Manager on this machine, Flink Task Manager on the second machine, and Flink Task Manager on all machines. It means when we depend our word count experiment on Flink Task Manager, it will yield all the Flink Task Manager in the cluster. And also it depends on the generator experiment as well on all machines, likewise. And also you can confirm what is bottleneck in your installation, because here it's very important for us to do everything efficiently and economically. So we don't want to waste resources. As you can see, your Flink Job Manager is kind of hot spot here. and it has some dependencies, well, like several dependencies. But it was good that we didn't depend our generator experiment on Flink, because otherwise these are also kind of they have many dependencies, and they're gonna run in parallel with Flink Job Manager. That you can always it's kind of visualizing your own design. So we have to wait a little bit here. It takes almost 12 minutes, I guess, to everything to get running. Now in the middle, I'm going to go back to my slides. We leave it here. Okay, so reproduce, we handle it in different layers. First, the infrastructure, which is like we use clouds. We support Google Compute Engine, we support OpenStack, we support Amazon EC2, and we also support in-house premises like bare metal that we just need to give IP address of your machines. So, but for Karamel, it doesn't matter where your machines are located. It could be in multi different clouds. It just treats all of them via SSH connection. Therefore, we handle infrastructure. So your cluster definition, if you design it for Amazon EC2, then later you can run it on Google Compute Engine. And then in the software level, we use Chef, as I said. Chef is a system for installation and configuration, and it's parameterized, so you can change parameters in your installation all the time. But it just supports a single individual machine. It doesn't support a cluster mode. So we leverage Chef, and we just use Chef recipes. In Chef, we have cookbook, notion of cookbook, which is like a package for defining your software, and we have some recipes. In each recipe is like when you define your services inside your software package. Like if you have Hadoop, you have Hadoop data node, you have Hadoop name node, or Flink task manager and job manager. And how we do it is like, for us, everything should be publicly available on GitHub. That's another way of making everything reproducible, by giving access to other people to use it. So, but you need to make your cookbook caramelized in a way that we define experiments in the same way that you define Chef recipes, and you have to define your orchestration rules in the cluster as well. Then Karamel makes sure that everything goes in the right way. And but inside Karamel, we have a cluster definition, which is like a simple text file. In cluster definition, you have name, and you define your provider, and you define your cookbooks. It's like importing your cookbooks. This provider could be Google Compute Engine, or it could be bare metal or OpenStack. And then you define your parameters here. And also in cluster definition, we have scopes. We have global scope and group scope. You see in the bottom part, we define groups. We have two groups, name nodes and data nodes. And we define how many machines you have inside each node and which recipes you want to install. You can define or customize your provider inside the group, or your attributes inside the group, which is like if you define anything inside the group, so group scope has higher priority than the global scope, so it will override the global scope. That's how you can have multi-cloud kind of clusters. So inside the core, we have DSL service, and we have some cloud clients. Given the cluster definition, the DSL service with cloud clients, they make a physical mapping of your cluster. And this physical mapping is the starting point for Karamel Engine to do the orchestration for you. It does the it builds a DAG, and it starts executing the DAG. And then our DAG, which is like our scheduler, which is DAG, follows this model. We have machines on different clouds. We don't care where they are. their virtual machines. And then inside Karamel system, we have queues per machine. So the scheduler will start running your DAG, and it will place the task that is ready to go inside the queue of each machine. And each machine has a separate thread for taking a task from head of the queue and run it on the virtual machine, and so on and so forth. That's how we make most of our cluster. We have the parallelization factor to the number of the nodes that you have in your cluster. And each task may produce some results, which is like shared. We have a shared memory design, and so each task will put the results in the shared memory, and the others will use it. Okay, let's go back to our installation. So, as you can see here, installation is still ongoing, and it's in the last step. So we can confirm, for example, we have now Apache Flink installed. We have our word generated. So if we just go back to this top menu, there is a menu called Quick Links. It's useful links of your cluster that is defined in your cookbooks. For example, you have launched the web UI for NameNode and launched the web UI for Flink. So I'm going to just press on the Flink. So you can see Flink Job Manager. This is the job that we ran. It's ongoing. We had 3 mapper tasks, 3 reducers, and 3 data sinks. In summary, 6 jobs are running and 3 jobs are starting. So it's going to take some time. But that's a very easy way to access your clusters, like utils, web UIs. And in the Hadoop, if I open Hadoop, you can confirm your cluster and a number of nodes, for example, you have different configuration of your Hadoop and stuff. But it's very interesting to go to utilities and browse the file system. In browse file system, I want to see what we have in the root folder. As you can see, we have counts and words in the root folder. I'm going to step in the words. You see we have 3 files, 128 megabytes, the block size is, and they are a little bit less than 100 megabytes, and they are named after name of the machine on the cloud. And if I go back to the root and go back to the counts, well, yeah, you see that the counts is also generated here. They are a little bit bigger, each of them, than the original file, because when you count, you include the number of counts for each word as well. And since I use the unified randomly generator, text generator, most of the word, 90% or maybe 95% of them are unique. So it will repeat all of them in the result as well. So if you go back to our orchestration deck, you see that it's finished, everything is finished. And we confirmed it by seeing the results here as well. And now we go back to the status. The status also, you see that everything is done, and you have logs and measure duration for everything. And that's what we wanted to do, that measure duration of, for example, this is the name node, the last one, and we wanted to measure experiment, word count experiment, which is 127 milliseconds, which is almost, yeah, like a little bit more than 2 minutes it took to do that. So the point here is that we design an experiment, we run it on cluster, and we measure the time. So the only thing for rerunning it is you have to do is, like, if you just click on the data node and increase number of nodes, and you rerun it again and measure the time. And similarly for other experiments. And you can also generate more sophisticated results. But here I'm going to show you some more slides. This I did myself offline. So I increase number of nodes, and I measure different phases of the running phases in Karamel, prickling, forking groups, forking machines, and less is the word count. As you can see, everything is quite constant expectation. So both Karamel and Flink run everything. It doesn't matter number of nodes actually. I increase it until 16, so you can see everything stays in the same order, because when we from Flink point of view, when we increase number of workers, I also increase number of blocks for the input text file. So we expect that it stay the same. And so finally, we have some more challenges and future work, and I'm gonna kindly invite everyone who is interested in this project. It's an open source ongoing project. Our source code is on GitHub, and we have very nice challenges. Basically, whatever challenges that you can find in distributed systems, you can find it in Karamel as well. First, we need to scale out our system. So we're gonna make it to run real clusters with thousands, many thousands machines. So scalability is the first challenge we're gonna solve. Fault recovery model is very important to not leave the cluster as if failure happens. So, and we need to have, we want to have expressive language for designing your experiments, and with a notion of time and like different stages that you have in your experiment. Instrumentation of the network is something that some experiments needs to have visibility about that. Elasticity and handle churn. Scheduling of if you have a shared cluster and you want to schedule your different experiments, how you do that in a fair way. And load generators and debuggings and recommendation systems that mostly help experimenter. We're going to support container-based machines as well, and result management from the raw results to the diagrams. That was my presentation. Thank you very much. I'm going to introduce our team members and thank all of them. First, Jim Dowling. He has not all just helping me with the ideas, also a lot of coding, and I'm really thankful. And Homan, he's PhD student. He did Google Compute Engine part for us, and Alberto, he does the OpenStack Nova support, and Abby, he did the AngularJS user interface for us. Thank you very much.